Okay, good morning, everyone. Thank you all for coming for day two. We are, good shot. Welcome back to Research Computing Leads Conference 2022. I'm pleased to welcome you all back for day two. I hope you've already gone and had some of the free coffee or refreshments that are upstairs in 9.57. This morning we have this is the wrong slide, so that's not helpful. This morning, this first session in here is some more of our research portfolio talks. Just quick order of service again. There is no scheduled fire alarm today, so if the alarm does go off, you need to go down the stairs to the ground floor, exit the building, cross the road, and if you could all congregate for me outside the light building, that is where we'll do a quick register to make sure we're all out and okay. If you have any access requirements related to that, please let registration know, and I'll make sure that is sorted out for you. If you have any problems during the day, please feel free to find us at registration or contact us via the Slack. Lunch will be here at 12 without any hitches today. And please feel free to, that again will be in 9.57. Please feel free to come and get some lunch up there. There'll be refreshments again at 2 p.m. There isn't a big interchange there, so you might have to pop up in like the 10-minute gap at the end of the session at 2. But please feel free to go and get some more refreshments as well. And without much further ado, I'm going to introduce Dr. Andrew Burnett to talk us through our first talk.
Hit share. That's synced up with everything. Excellent. Okay, so thank you very much. So I'm Andrew. I'm from the School of Chemistry, and my group concentrates on looking at crystalline materials and understanding their vibrational dynamical properties and calculating spectra of those materials. So my background is actually an experimentalist. So we started measuring these spectra, particularly at the low frequency end a few years ago, and then we didn't really understand what those spectra meant. But we got some nice sharp peaks, and then I spent the last 15 years working out how to calculate them and trying to do it faster and faster on bigger and bigger systems. So I know some people in the audience will also use similar codes, so I'm just going to quickly give an overview of the kind of codes that we use on ARC. I'm going to give you some examples of why calculating these vibrational phonome modes are really quite tricky, and some key examples that we've done very recently. So in particular, it's not just about calculating the spectra, but then it's going from that calculation to what you actually measure and trying to join it up in the two. Sometimes it's easier to try and do something with the experiment to make it simpler, and sometimes it's about adding extra information to the calculation to move to the experiment. But the key for me is always to be able to use these calculations to interpret my experiments. And then hopefully in the final few minutes, we've also been developing a GUI based in Python to post-process a lot of these calculations and do a lot of the interpretation, because really the key is to be able to get it to the point where experimentalists can use these methods to interpret their own measurements. So I use a whole range of different codes. CASTEP, VASP, and Crystal are all density functional theory ab initio based solid state calculation tools, and we switch between these depending on materials, or we spent some time comparing them to try and understand what we wanted to do. Very recently, we've been doing some molecular dynamics calculations, which I'll talk about at the end. So that's all about watching these materials change as a function of temperature or pressure, and then using those to calculate spectra. And then in between are some various tools to do some of the pre-processing, or to try and, in particular, I'll talk about FNOPI for a couple of minutes, and that's all about trying to get calculations running as fast as possible on ARC. So cheating and trying to split these calculations up to make them as efficient as we can. So a couple of years ago, we published a paper, and about 3 or 4 years ago before that, we started calculating the spectra of this small material. So this is these sodiums, sulfurs, and oxygens, and it's a bit of an odd material, and we thought it would be a good test base. If we could calculate this well, then we could understand quite a lot of things. And this is our first attempt, just using some different codes, putting the structure in and changing some things and calculating the spectra. And every single one of the spectra are completely different, and there's no correlation between them at all. And it just shows that this is still quite a tricky problem. What if you put rubbish in, you'll get rubbish out, is the key take-home message. But what each code thinks is rubbish is slightly different. And therefore, you really have to have a feel for each code and really be able to understand what's going on and be able to do these calculations, particularly in this low frequency region that I'm particularly keen on. So we've looked at all sorts of methods, and this really the take-home message from this is we ended up doing 22 different calculations using different codes, different functionals, all sorts of different things, turning things on and off to see and try and understand the correlation. So this plot here is really trying to group the calculations into similar calculations and trying to understand why a particular set of calculations would give us similar results. And a lot of it is down to the software that you pick in the first place. The software has been designed in a particular way, and you can end up getting the same results from different software as long as you know sort of the aim of that software in the beginning. They use different basis sets, which is the way we estimate the wave functions where the electrons are, and each require their own requirements. So one thing in particular we found for CASTEP is that we can calculate the spectra, and there's something called a fine grid scale in CASTEP. So we perform these calculations over grids, like many calculation methods. CASTEP has its own particular grid to look at the electron density. And with this, if you change the grid scale, the cell size basically doesn't change, the cell volume basically doesn't change, the energy of the system doesn't change, which is the kind of thing we would normally look at to check for convergence. But actually, the phonon spectra changes quite dramatically. The key is you wouldn't have any idea which of these were right unless you had the experiment to compare it to. But actually, we need to compare. We need to go to a very, very fine grid scale. So to put this into context, a fine grid scale of 6 takes about 10 times longer to do this calculation. So you're talking a week up to 10 weeks. I don't use CASTEP anymore at the moment. But generally what we found as a rough rule of thumb is the very low frequency acoustic phonon in any code should be about 10 wave numbers. And once you get to that point of convergence, however you end up with that convergence, you're probably at the accuracy you need for experiment. So we learned that correlation between experiment and calculation is very dependent on the basis set and pseudo potential. So that's the wave function that we use. And that is you can't use the same one for each code. So that basically means it's very dependent on the code. So for instance, Crystal uses these Gaussian basis sets, and some of the ones they supply by default don't work very well for these calculations, and you would need to optimize them. Modern dispersion corrections. So corrections that deal with very weak forces in our material are crucial with these calculations. If you don't turn them on, they won't work at all. But basically, we got to the point where we got nearly identical spectra from the 3 main codes. And these are sort of the big codes. CASTEP and VASP are 2 of the, if you go and look at Archer 2, they're the 2 of the most popular codes on those kind of systems. But the subtlety in what you need to change is difficult, and also comparing these codes is non-trivial. So Crystal diagonalizing matrices in a different way from all the other codes. VASP uses different masses for your elements from all the other codes. So we ended up having to develop some software that allowed us to do the comparison easier and try to figure out what was going on. So that's the calculation side of things. But then we don't actually measure a single unit cell of material. Often what we measure is a powder. So we take our material, our little gray balls, and we pack it into a different material to make it a nice stable material, and we put that in the beam and do the measurement. So how does this affect the spectra, and how do we get from our calculated peak positions and intensities to a real experiment spectra? So we can do something called an effective medium approximation that allows us to take these things into account. It also matters that all these particles are charged and they're randomly orientated, and the charges actually affect the spectra. In some cases can shift those calculated modes by quite a substantial amount. So just as 2 examples, this is the same material but infrared frequencies. So the black line is the experiment, and if we take our Maxwell-Garnett effective medium approximation, which is just one of the effective medium approximations that is commonly used for a whole range of things, we can use that to calculate the powder spectra. And the only thing we haven't calculated here is the peak widths. We've taken the peak widths from experiment and used that as part of the in the fitting process. But you can see basically very good agreement between experiment. At the lower frequencies, the Maxwell Garnet doesn't work as well, and we're still not entirely sure why, but there's another effective medium approximation that we can play with. But in this case, we also need to take into account the little gaps between our spheres, because that actually causes this rising spectral background that we see in our spectrum. So we can play with things, and we can really begin to get really quite good correlation between our experiment and our calculation. The other alternative, if you don't have a powder, is that you'll measure a crystal. So you'll take a crystal, you put it in the beam, and it will have a certain orientation. So you'll send a beam in, you might measure reflective, you could change the angle here, or you could rotate your crystal round, or you could look at a different face. And we can now, just recently, we've introduced this into our tools so that we can calculate the spectra as a function of rotation angle, or if you grow a crystal that has a different face, you can, which are governed by these numbers here or described by these numbers here, you get a different spectra depending on what you're looking at and depending on the polarization of the beam that you can get in. So we're now getting closer to, again, if someone says to me, I've got this crystal, I've measured the spectra, I can ask them about what cut of crystal and how thick it is, and we can start to do that. So the final calculation that I want to talk about, I'm really using this as an example of how we now do things on ARC. So cysteine is one of the common amino acids. It's got a bit of a strange crystal structure. So if you cool it all the way down to 6 Kelvin, all of the cysteine molecules are bonded together like this. But as soon as you start to heat it up, you can rotate one of the bond angles and you get two different bonding configurations. So you get essentially disorder within our crystalline structure. And this disorder affects the properties of this material. So if we just take these two structures, the two extremes, and we calculate the low frequency spectra, we can see that they're different. So we should be able to tell that difference. But neither of those two spectra correspond to experiment at all. So we're probably somewhere in the middle. And that's where it gets a bit tricky. So what we tried to do is develop these supercells. So instead of the unit cell, which has one molecule in, we now have 32 molecules. And they're arranged in different packing orders. So this has a 50-50 mixture of those two different configurations. And then we need to calculate the spectra. So the problem is that we've now gone from 30 atoms to 500 atoms. We've done everything we shouldn't do. You've made a really big system. You've broken all the symmetry, which is how we usually cheat and make calculations a bit bigger, a bit quicker. We have other problems in that parallelization is usually done over what are called K points, which are dividing this up. And usually you need quite a small system to have a large number of K points. You also parallelize over bands or G factors. So that's basically how many electrons. So what you want is really heavy elements, and we've got really light elements. So pretty much everything you shouldn't do. So what we do in the previous calculations I've shown, we basically plug our structure into VASP. We do an optimization. VASP calculates the frequencies, VASP calculates the charges, and we plug it into our own software to get the spectra out at the end. Now we can't do that. One of the reasons we can't do that is VASP doesn't have a restart functionality for frequencies. So if you can't calculate it within 48 hours on, or whatever your queue time is, then you can't do it using VASP. That's where FONOPI comes in. So what FONOPI does is it takes your structure and it displaces those structures into a range of structures. You calculate the energy of each structures, and then FONOPI can build that back together to calculate the frequencies. So in this case, this generates, I think there's about 1,200 different structures, which you can then all submit as separate single energy jobs. Each calculation takes about 24 hours on a single core. So you can spread that across ARC. And also that tends, because you're running all of them on a single core, you kind of fill in all the gaps. So actually they run very quickly. The only thing we have to do with VASP is to take the static structure and calculate the charge. And that can still take on a single node 48 hours. But we can run through those as well, and then we can plug them back. That gives us a structure that's not moving, but we get the spectra out of it. For these big systems, what we started doing is looking at dynamics. So molecular dynamics is a thing that lots of the physicist chemistry community do, and we can still get the spectra out of a molecular dynamics run, because essentially all we want to know is things moving, how fast it moves, and where the charges go when they move. That's where we get our spectra from. So we can do some initial molecular dynamic steps using CP2K to get the structure that we want, and then we do a long 30 picosecond run. So at the moment we run these on ARC3 because the queue's quieter, and we can run these on 24 cores and they take about 3 weeks. Okay. The problem is we then need the charges. The charges take a while to calculate, but you can do that trajectory, split it into little jobs, calculate the charges at each point across hundreds of nodes, and then plug it all back together and get a spectra. This ends up with files of up to 1 terabyte in size, even with state-of-the-art compression algorithms that CPTK use. So we're now running into storage problems, but that's a problem for another time. So with the two calculations, you get very similar spectra in the mid-IR. These are the calculated spectra. This is an experimental spectra taken from the literature. There's a slight shift in peaks because the dynamic also has the advantage that it takes into account something called anharmonicity. But at low frequencies, the dynamic calculation is much closer to experiment, and that's because in that disordered system, it's the things that are moving around and the fact that those torsion angles can also rotate changes the charges, and that gets us much closer to experiment. So in the last couple of minutes, I just wanted to show something called pdialect, which is a tool that we've been developing over the last few years. It's essentially a generic Python parser that will read in DFT calculations and put that into Python for you. It also has a GUI because we want to get master's students and undergraduate students and PhD students who have never done computational chemistry before to be able to use it. And it allows us to introduce things like the effective medium approximations, particle shape. It's available on Conda, Pip. It's on GitHub. Anyone can freely go and use it. And then hopefully, so this is what it looks like. So you can change that drop-down menu there and read in any type of computational file, and it will read it in and parse it and spit out some information about the unit cells and those sorts of things. We've got that set up in terms of a settings and then a series of scenario tabs that you can add or take away. The key ones are the first scenario tab will set up a powder calculation, and you can change the shape of the particle, the crystal orientation of the particle, those sorts of things. Or you can also set up a scenario where you take your crystal, you tell it what angles it are, and it will calculate it. And then it will read all that into the plotting tab. So here are this is fluoroapatite. All these files are available on GitHub as well. And this is fluoroapatite looking at different crystal orientations packed into it, different crystal shapes and sizes packed into a powder, whether they're plate or spheres. So they're shifting peaks by quite a lot. So you need to take this into account when you're comparing to your spectra. And if I switch to my crystals, these two lines here are different thin films of crystal orientated at different angles. And this horrible line here is what you would get if you just took a slick, thick slab of this material and fired a measurement beam into it. So again, it's completely different from the calculation, and you need to know where the calculation limits are and how to get to it. But also my favorite bit is that it also allows me to animate all my vibrational modes. And so I can visualize my structures, and I can save these as movies. So these are the movies that I end up putting in my normal science talks when I'm talking and presenting about these materials. So this will export as MP4s and pings and structures and all sorts of other things. So, and really this tool came about from the comparison of the different codes. We needed a single way of being able to read that in, get it into the same format, and being able to do a direct comparison. Okay, and with that, I will stop.
Thanks so much, Andrew. Well, next up, we've got Michelle Morris. So we'll just set that up. That's actually, we're doing questions at the end. Scenario should come through the speakers. Super.
Thank you.
There we go.
Cheers. Well, hi everyone, and thanks for Alex for inviting me. So I'm going to just start with the problem. So I don't know if, or the problem that our team are working to try and do something about. So is everybody aware that 1 in 7 deaths in the UK can be attributed to poor diet? It's a pretty shocking statistic, isn't it? And that 30% of all human-made greenhouse gas emissions are caused by food production. So I just want you to kind of bear those in mind as we go through some of the examples here today. So I'm Michelle Morris. I'm an associate professor in the School of Medicine in Leeds Institute for Medical Research at St James's, but sit within LEADER, and a fellow of the Alan Turing Institute as well. So there's loads of affiliations on the right-hand side there, but they're all really important to the context of the work we're going to talk about. So as I said, I'm based in LEADER up on level 11. I'm a co-investigator with the Consumer Data Research Centre, and we have quite a substantial healthy lifestyles strand within CDRC. And then I lead a team in nutrition and lifestyle analytics. So thinking about those stats about diet then, so why is that so difficult to change? So partly not everyone's fully aware of the scale of the problem, but we all eat, we all shop for our food, pretty much all care about our health and the health of people around us, and most people care about the planet, but yet it still continues to be a huge problem that's growing and growing. So part of the reason it's so challenging is if we think about the food system, it is really complicated. So from things like the food chain and agriculture, all the way through to the environment within a supermarket where you find the foods, how it's designed, general access to different places, which is what you see on the left here. But then on the right, this is all the government policy departments that are responsible in some way for food. I don't know how well we think the government collaborates and government departments, but I'm pretty sure that all of those different departments are going to find it hard to actually come together and have one approach to solving these huge problems. So this has been in the news quite recently, so maybe more people are familiar with it, but last year, or a couple of years ago, the government commissioned Henry Dimbleby to do an independent review of the food system. So the part 1 was in July 2020. They finally released the kind of master plan in July 2021. And then almost a year later, the government responded with what they would endorse and what they wouldn't. And there was 14 recommendations within the plan, and they've kind of said they'll do a couple and that they'll set up partnerships to address a few more. But the one that I want to zoom in on here is that there was a strong recommendation to create a national food system data program. And it's something that I think is so important to all the kind of problems that people are having within the food system, within kind of nutrition research and nutrition related challenges in health and all the way across the system, different businesses. So what they said was that they would support a food system data transformation partnership. I am not entirely sure that that means that they're going to fund the big data program that they need. Like in my head, I see this, needs a really substantial investment. But what is happening is that people are coming together and those government departments are starting to talk, and they're currently consulting experts to work out how we might be able to get data in one place. And the reason that some of this is really important is that traditionally, and I say traditionally in that like it's still happening, it's not completely in the past. If we want to make decisions around diet or understand dietary behaviors, we sit people down and ask them to complete food diaries. If there's lots of money available, you might interview people. This has moved to online equivalents in maybe the last 5 years, and then that kind of automates it a lot more. But there's very much the burden is on any policy making, any decisions around food, you collect the data yourself. So I don't know if anyone's ever actually collected their data on what they've eaten themselves. I try and do it quite often, and it's really hard. Like, you forget, or there's something available. So, it's a huge burden, but we're generating information all the time at a huge rate on what foods we're purchasing. Hands up who's got a loyalty card. Yeah, who pays by card in wherever, when they get coffee, when they go to the supermarket. Yeah, so all this data is getting generated. And it is possible to access these sorts of data and to start linking them together. And that's some of the work that we do in the team. So it's quite a broad spectrum of the sort of work we do, from looking at food environment using open and GIS data and the activity environment. So I'm not going to speak much about physical activity or at all today, and focusing on the nutrition stuff. We've done a lot of work on the validity of different data sources, especially newer data sources that haven't been used in this context before, and consistent reporting of these sorts of data, how they then impact on health outcomes, and thinking about inequalities. But the majority of the work now is using novel forms of data, like till receipts, like transaction data from supermarkets, to be able to better understand the diet-related behaviour. So not just what is available, what people can access, but what they do access are recorded through what they've been buying. So an example of this from open data is looking at the eligibility and uptake of free school meals. So lots of people are eligible. This on here is the different regions in the UK, and eligibility is the whole plot, but the dark sides on the darker bits on the edges is where people didn't actually take those meals. So we're looking not only at what's available, but what the behaviour actually is. So there's a problem there that's not been taken, and we can see it clearly from the data. We were looking at this in the context of Bradford, so we zoomed into Yorkshire and the Humber, and so we've got Doncaster, Bradford, Sheffield, and all the way across. And I think what you see here is the behaviour is not uniform. So while there's variation according to those that are eligible in the first place, but uptake's not uniform either, and the distribution of the people in the different areas varies, and we can see that spatially as well. So here's a map of Bradford on the right hand, the bottom here. So we can do really important things with data and translate them to policymakers, and this was done for a community in Bradford. Another engagement example, which is something which is still ongoing, is with Leeds City Council, who were interested in the carbon footprint of their school meals. So we've been able to work with them. They've shared their recipe information for all the meals in schools, and also the transactions, or what the children chose over the 6 weeks period last year across 5 schools. And we created an automated dashboard in our Shiny where they can drop in the recipe information, press a button and get out the carbon footprint, and then download that. And what Leeds Catering Services are doing at the moment is actually using this to look at how they can swap out ingredients to lower the carbon footprint of meals. But it was for school kids, so we also done some engagement with the kids and taken that information about the popularity and the carbon footprint of the meals, and have gone into schools and done some 2 lots of 2-hour sessions. And one of the things we've done is create this Planet Plates game, which you can play yourselves and see how well you understand different recipes. But it takes in things about the carbon footprint of the meals that actually are on their menus at lunchtime, and also the popularity of them. So they can work out which one's most popular, which one has the highest carbon footprint. And the idea here is that they're learning about carbon footprints of food, and actually we're giving them some tools to try and do something about it. Because I think, it's a huge problem that I posed at the beginning, and it's taking complicated data and making it accessible to people. And we're dead excited about it. And we're extending it into health metrics at the moment as well. And it's likely to be used by the university, and also, with a bit of luck, the Teaching Hospitals Trust. The other big thing we're doing, moving into much bigger data sources, is working with commercial partners. So I've been the academic lead for the strategic partnership of the university with Sainsbury's, and last week we announced a strategic partnership with Asda. I'm also funded by the IGD, which is a social impact organisation that works with retailers, and that's to look at evaluating the impact of trials on healthy and sustainable diets in retail settings. So on the computing side, so those of you that know, this is a map of the old secure data system in LEADER, but it's a very similar model that we have now in LASER, which is the Leeds Analytics Secure Environment for Research. And this is something that I present often to industry partners to build that trust with them and explain how we will use their data and how it remains secure. And that is a huge chunk of the work I do. And while it's not necessarily research computing as such, it's fundamental to being able to do the work that we do and being able to translate that. And it's really important for them, not only that we have ISO 27001, retailers aren't that interested in the NHS DSPT, but they also have their own third-party assessments. So despite having an ISO audit 1 week, we still have a retailer group come in the week after to do another full audit. And it's, you know, being able to bring data in through an independent team before it gets to the research service, to the research team for analysis, and being able to reverse that to secure that any outputs that come out and are shared go through a thorough process. Laser has been great as well in that, like, we have a VRE, a virtual research environment for each of the different retailers that we work with. So there's no kind of crossover with the data there. We've got set up where we have different size number of cores. So we have kind of 8 cores as standard, some 12 core machines. Recently, we've been able to, you know, boost up to, you know, doubling the size of the actual computation in there for a period of a month where there's been a high intense processing, and then drop that back down again later. And then these are some examples of the work we've been able to do for using this setup. So here's some work from Vicky Jennison's PhD, which was looking at purchasing patterns of fruit and veg across Leeds. So hopefully most people know a little bit about Leeds on the right hand side, but those kind of northern areas are more affluent and rural, and we see, perhaps unsurprisingly, that there's more fruit and vegetable portions purchased in those areas. We also see that there's over 1.5 portions per day difference between the least deprived and the most deprived, and then the average household purchases in Leeds was just over 3.5 per day. So the difference here is that with loyalty cards, they're buying for potentially a whole household. They could be buying from multiple places, but it could be for a household. That could be 1 person, it could be 5 people. So it's 3.5 when the daily recommendation is 5, is even lower than it sounds. Our national surveys are suggesting 4.2 and 3.8 portions using self-reported metrics. So perhaps people exaggerate a little because they know they should, whereas we don't get that with retail data. So there's pros and cons to all the data, but what we've learned is that there is value in understanding population behaviours using these sorts of transaction records. This is a little bit of a busy slide, but here we took a year's worth of transaction data and used k-means clustering to look and identify different dietary patterns that actually exist within the data. We can see clusters like those that have a lot of fruit, people that buy lots of meat alternatives, carnivores, people who buy loads of bottled water, and then beer and wine lovers and a sweet tooth. So some people's dietary patterns is dominated by their alcohol purchases, others by kind of sugary sweets and drinks. And then we've been able to profile that against information like nutrition information. We've been able to look at it by IMD deciles and supergroups, which you know, starting to unpick potential inequalities. And then we've got examples from trials that have run. So this is some of the IGD work, and what we've got here is almost 2 years of data, just over 2 years of data of fruit and vegetable sales across 101 Sainsbury's stores in the UK. And in the green bars in January 2020 and January 2021, they promoted various different fruit and veg by incentivizing, reducing their price to 60p. If we consider January 2019 as a baseline, you can see that for those promoted items, there's a huge shift up to 78% on the promoted items there. You know, it's really complicated because we've had a pandemic, everyone's behaviours changed completely. So you can see the red in the bottom. And in the second year they did this, they promoted less items and were in a period of lockdown. So it didn't appear to be as effective. But we've been able to then go on from this and look at impact on the wider basket, do interrupted time series analysis. So this is just some of the really early stuff. But just to give you a flavour, that was analysing 23.5 million baskets, which contained 1.5 million baskets of the promoted items, and all of this resulted into 4.9 million extra portions. So it's huge, and that's from 101 stores that ran the trial in both years. So there were more data to start with before we kind of distilled it down. And then just one last bit of work to leave you with. So there is obviously a kind of a bit of an ethical component to these data. So the data are used without, so it's always anonymized or non-identifiable information that comes from retailers to us. And it's always held securely, but it's done through us being a trusted partner that are accredited and can demonstrate that we had to hold the data securely, as opposed to a very specific consent where somebody says your loyalty card data will be sent to the University of Leeds. You've ticked that in your terms and conditions about sharing with trusted research partners. But we really wanted to understand what the public think to these sorts of data being used for research. So this is some primary data collection that we did a couple of years ago now at Leeds, where we surveyed over 7,000 people, sort of from the trust, from different kind of social media ways of recruiting, of GP practices. So Leeds City Council helped us out, and we found that and the question that was most of interest was finding out whether people use loyalty cards and fitness and health apps, but also whether they'd be willing, hypothetically in the future, to have them linked to their health records, because ultimately that's what we want to do here. So we want to be able to understand and promote healthier, more sustainable diets, and then actually be able to better understand the impacts on health and the health of the planet. So while 70% of people reported using loyalty cards, just over 50% said that they would be happy in theory for those to be linked to health records in the future. And of those that didn't say yes, 30% said no and 17% were unsure. And we collected quite a lot of free text data as well there. So we've been able to do text mining and to look more closely at that to sort of understand the barriers. And there's a nice paper on LDA in JMIR. But different for health and fitness apps. So less people use them, but much more people would be willing to share the information from them. And that's not something that we initially thought about when we started doing this work, or realized that would be a case. But it makes perfect sense when you see it like that, because they're very different behaviors. So we use people use loyalty cards to get discounts, to save money, to be promoted the things that they want, not necessarily from a health point of view. Whereas if we're using a health and fitness app, we care about what we're doing already. So they're quite different, but this has been able to help us going forward with kind of the hope for the next stage of the research. And we were able to look at attitudes within different subgroups as well. So we can see that men and those that are 18 to 25 were much more likely to say yes, and that the Asian population were more dubious about sharing. And this, with health and fitness apps, it was much higher relative risk ratio of the younger people wanting to share or being willing to share their data. So that is a bit of a whistle-stop tour, and I think Alex wants us to do questions at the end, don't you? So thanks everyone for listening.
Great. Thanks so much, Michelle. Fantastic. So that's where I need to get myself in order. So our final speaker for today is Professor Susan Grant-Muller. Can you hear us, Susan?
Yes, I can hear you. Thank you.
Super. This talk we're not going to feature on the live stream, but we will be back at 1 p.m.